So yeah, what we wanted to do in this project was to actually work on zero knowledge proofs, and then on the side we noticed that this actually turned into a really efficient digital signature scheme. So this is a project with quite a lot of people, all of whom you can find on the slides here. I hope I didn't forget any of my co-authors: Leonard Lenz, Peter from Oxford University, Emanuela from Bocconi, Sebastian from AIT, Christian Mainz from DTU, Shibam, Christian from TU in Graz, Michael in Finland at Aalto University, Cyprien at COSIC in Belgium, and then Ward at IBM Research in Zurich. So quite a distributed project in Europe. Also, let's do it like in the previous session. If you have any questions, just raise your hand and interrupt me this way. Please don't just shout. And ask for the microphone. Yeah. So let's get started, and let's hope that the clicker works. So yeah, this is based on 3 papers actually, or 2 papers and a specification. So what I'm going to talk about is, so some of this has appeared in a paper at Crypto in 2023, and with a subset of the people I mentioned. Then what I'm talking about is also partially in the algorithm specification for a NIST PQC additional submission, round 4 submission for post-quantum signatures for an algorithm called FAEST. And then there's a recent write-up that you can find on ePrint with some more results that we put together, extending the what we had about this FAEST signature scheme. And even though this talk mentions voles, I can assure you that no voles were harmed in making these slides and also doing this research. And I also want to thank my collaborators Lance and Leonard, who originally made the slides and that I stole for this presentation. So, you know, if you like the slides, that's because they made them. If anything is wrong on the slides, that's because I modified them. So there's that. Okay, so why am I? So I'm going to talk a bit about zero knowledge proofs, which doesn't really sound like, you know, what does this have to do with post-quantum cryptography? But I hope that by the end of this talk, I'll have you convinced that this is indeed important. And as many of you know, zero knowledge proofs, digital signatures, you know, a lot of signature schemes are essentially just zero knowledge proofs. So there's that. And I'll begin by introducing something called VOLE-based zero knowledge, and then I'll explain how this relates to the signature scheme called FAEST. And we have to begin by thinking about, well, what kind of zero knowledge proof systems are out there? So just all of the succinct stuff that people love when you talk about blockchains and whatever, like Ligero, Starks, Roth16, you name it. This is not something I care about, and this is also not something I care about in this talk. So what I'm looking at are proof systems that are really, really fast. So where the prover runtime, as you can see here, is rather low. And then they might have a bit larger proof size. The proof itself will be of a size that is proportional to the statement that you want to prove in zero knowledge. But that also might not be as bad. The reason is, so all these succinct proof systems usually, so the proof is smaller than the statement that you want to prove once the statement is big enough. Like you have some startup cost, and this startup cost makes them also infeasible to use for digital signatures. Usually the startup cost for such a proof system, like to make a proof or make a signature, is just bigger than whatever you can do with other proof systems that are not as fancy, but where making the proof is just a lot faster. So, and this is where VOLE-based proof systems fall into. They are kind of in the same category as MPC-in-the-head based proof systems. They're kind of an extension of this, but they actually optimize MPC-in-the-head based constructions quite a lot. If you think MPC-in-the-head and post-quantum signatures, you might remember Picnic. What we're doing is going a bit along the lines of what Picnic has been doing, but quite optimized. And if you I guess I'll leave that comment there on the side out. Okay, so VOLE in the head and VOLE-based zero knowledge. So before we put the VOLE into the head of somebody, let's figure out how we do VOLE-based zero knowledge, so you understand how these proof systems work, and then we can kind of adapt them to make them non-interactive, so we can use them as digital signatures. So let's lay the foundations here. As you know, in a zero knowledge proof, there's a prover and there's a verifier, as they are depicted here. And if we want to use VOLE-based zero knowledge proof systems, we first have to understand what a VOLE is. So as I mentioned, these are also little rodents, but for the purpose of this talk, a VOLE is a so-called vector oblivious linear evaluation, which is a special type of correlation between the prover and the verifier. So you have this magic box here, and that generates a vector u and a vector v for the prover, or the prover inputs a vector u and gets a vector v out. And the verifier inputs a vector, inputs an element delta from some underlying field, and it also gets a vector out, which is u times delta plus v. So it's a lot of linear equations that are being generated here. If you think about it, so these are correlations of length n. The prover gets out n linear, so just n degree 1 equations, and the verifier asks for an evaluation of all of these lines in point delta, and it gets that point, and gets a vector of these evaluations in that same point. And this is what a VOLE correlation is. There's one side, the prover, that gets two vectors, and there's the other side, the verifier, that in the end has one value delta and a vector q, which fulfills this kind of equation here. Okay, so far so good? Okay, very simple. And it's called vector OLE because, you get a vector where this delta is fixed everywhere. For all of these instances, you get an evaluation in the same point. Okay, and if we talk about zero knowledge, we kind of have to ask where can we get these correlations from, and there are actually quite a lot of algorithms that have been built in order to construct vector OLE. For example, from oblivious transfer, homomorphic encryption, learning parity with noise, and so on and so forth. So there's quite a lot of stuff, but I'll leave that out because we're not going to need this if we want to build signatures anyways. Okay. So the great thing is that once you have a VOLE or a lot of VOLE correlations, you can easily build a zero knowledge proof system. Why is that? The reason is that VOLEs are actually linear commitments to this vector u that you have here. So as you may remember, the prover has u and v, and the verifier has a point on each of these lines, and this essentially commits the prover to this u vector. Just making this correlation means that at the end the prover is committed. If you want to open this commitment, well, the prover sends u and v to the verifier, who just checks using the value delta and the value q that he has that this correlation holds. Okay, so opening is simple. Well, why is this commitment hiding? We have that q is u times delta plus v. Q is delta is independent of all these correlations, of all these u and v values that the prover has anyways. And the value q is always blinded by this value v here that is uniformly random. So also when you make these commitments, the prover, the verifier has no idea what is in there before you open them to the verifier. Okay, and then why is it binding? This is actually just a simple exercise that you can show that if a prover would be able to open a commitment to two different values, it would have to be able to guess delta in advance, which it can't because this VOLE box doesn't actually reveal delta to it. So there's that. Again, this is something that you can easily find on any paper for vector OLE based zero knowledge proof systems. How to do this is the two-line proof. that you can do on a whiteboard in the break if you want to. Okay. Anyways, VOLE correlations give you commitments, so that is great. And in particular, they give you linear commitments, and linear commitments is what you want to have if you want to build a very simple homomorphic, a very simple zero knowledge proof system. Well, why is that? So why is it linearly homomorphic? First of all, well, that means that if you have two commitments to some values, you can kind of smash them together and generate a new commitment to something that is related to the committed values in the original commitments. So for example, if the prover has two commitments, let's say U1, V1 and U2, V2, and the verifier has delta and two of these Q values, two of these evaluations and some points, then if we make alpha and beta public, then we can very simply generate a commitment to the secret alpha times U1 plus U2 plus beta. And this is just by the verifier having to adjust, the verifier having to use alpha and beta and the Q values that he already holds to generate a new value Q, and the prover can also make some local computation, which allows it to generate a new commitment based on the, related to the secrets that it had before. So this actually means that we can do homomorphic operations on committed values. And once you have that property, then this just always directly gives you a very simple zero knowledge proof system based on a paradigm called commit and proof. And how does it work? Well, you want to, in the zero knowledge proof, you want to prove some statement about some kind of witness that you have, at least in what we call a proof of knowledge. So this is what is gonna be going on here. If you want to use this commit and proof paradigm to build a zero knowledge proof system, what do? Well, you commit to your, you first of all make a lot of VOLE correlations. You use these to actually commit to the witness that you want to use in your zero knowledge proof system. And then you evaluate the circuit which proves the statement that you want to prove gate by gate on the witness that you have. It's called a commit and proof paradigm. You have your witness, you commit to the witness, and then you prove the statement kind of gate by gate fashion. And if you have linearly homomorphic commitments, linear gates are very simple to do. So gates here, I mean an arithmetic circuit that has addition and multiplication gates, nothing else. And these addition gates, or let's say linear gates, are very simple to do because we have linearly homomorphic commitment scheme. Here, multiplication, well, this is where things get a bit more tricky. There have been generic techniques out there using so-called multiplication triples, but this is rather inefficient. So we will try to do a bit better. Okay, but we'll follow this kind of paradigm that has been tried and tested since like ages. Okay, so let's see how to do multiplications. And here I want to stress that this is not something that we came up with for FAEST or so. Using these VOLE-based, these VOLE correlations for zero knowledge is something that actually already appeared in the paper in 21 in crypto, and some parallel work at CCS, I believe, by Xiao Wang and his group and his team. Really great work by Xiao, and in parallel, what we also did something there in this regard. And this is completely independent of post-quantum crypto signatures, whatever. Anyways, there, okay, now, as I said, linear statements, very simple. Multiplications. How do we do multiplications if we have VOLE correlations? How can we prove something about something being a commitment to the product, and that this is actually correct? And it turns out for VOLE correlations, this is actually quite simple. Well, why is that? What you have is you have two inputs to a gate that you're committed to. So, you know, there are two commitments, and both of them are to one of the inputs that go into the multiplication. So let's say the prover also wants to commit to the output of that and show that this is indeed correct. And once we have that, we can just prove any statement we want to have. And now the crucial observation, or the super simple observation made by Dittmer, Ishai, and Ostrovsky in 21 is that, so well, what happens if you multiply two lines? Right, so a VOLE correlation is a line, as I said. What happens if I multiply these two lines? Huh? So each line in the degree 1 coefficient held the secrets of the commitment, right? So if I multiply these two lines, I get a degree 2 polynomial that holds, surprise, the product of the two secrets, right? Multiply two lines, I get a polynomial of degree 2. Okay, great. So if the prover now commits to the product as well, right? How can we check that this degree 1 equation where the prover committed to the product is the same as what is here in the in the quadratic polynomial? Well, the prover can multiply this degree 1 polynomial with x, so the indeterminate there, and it gets a degree 2 polynomial. And if it subtracts this from the product polynomial, then you get a degree 1 polynomial if and only if if the secret is the same, or if the prover actually committed to the right product. So this is what we're going to use for the multiplication check. So here's so this multiplication is, as it turns out, an operation that the prover and the verifier can each locally do on the values that they have. And doing this operation here is also something that they can do locally. And then what we have is that all of this, what we get out of this, is going to collapse to a degree 1 polynomial if and only if the prover wasn't cheating. And this is something that we can then just open and check. So the prover can reveal to the verifier that indeed it held a degree 1 polynomial such that this here holds, and this way it will be able to convince the verifier that it committed to 3 values A, B, C such that A times B is C. This is rather straightforward. Of course, you kind of have to mask this so you don't reveal any secret information to the verifier. Oh well, that's simply done. Okay. Again, why this works is actually something that you can just write out by hand or find in this paper at ITC 2021 by Dittmer et al. Or also it's just something that you can check on a whiteboard if you feel bored. The main point here being there's a very efficient way of checking for VOLE-based commitments that multiplications are indeed holding, or a multiplicative relation is holding on committed values. Yes.
Thanks. Just a simple question. Is this different from quadratic arithmetic programs? It looks quite similar, but I think they were around since about 2014 or so.
I think as with a lot of cryptography, it gets reinvented in a different field later again. Also, a similar trick has been used in lattice-based crypto independently. I think what Dittmer et al. Didn't notice is that this was around in co-ops before, like 2013, 2012, or so on. So yeah, very likely I didn't look into these old papers actually, but you're not the first person to notice that. But
okay,
thank you. Yeah, as I said, vanishing coefficient technique. Yeah, it's known in the ZK community for quite some time already. Rediscovered. Attribution missing in 2021. Okay. Anyways, so if you have VOLE-based commitments, that means that there's like you can now do additions, you can do multiplications, so you can do anything you want on your witness to prove something. So yay, we're done, right? So let's first of all think about how expensive is it to do these kind of proofs, and that's why they're actually quite great. So first of all, you need to generate these VOLE correlations, and actually you can generate L random correlations with less than L bits of communication based on LPN-based constructions and so on, based on pseudo-random correlation generators and all these funny techniques that have been developed in the past 5 years. And then, well, for if you want to commit to the witness, you kind of have to send one field element per witness field element. And then for each multiplication, you have to send you have to commit to the output of the multiplication. Well, the inputs are already there. And you have to do nothing for the linear gates. And in the end, you don't just open kind of one product. If you want to do a check, you can amortize over all multiplications in the circuit. So you can amortize that as well away as well. So if you have a circuit with m inputs and n multiplications, you kind of pay in communication m field elements and n additional field elements, so m plus n for proving a statement plus 1 to reveal the output, which is essentially optimal. So that's great. Like, so there's no hidden constants. Like that's what you pay. So fantastic. Now I've been talking a bit about this VOLE stuff now, right? And there's this delta that the verifier has to keep, and the binding of the commitment scheme, the binding property, is kind of crucially reliant on the fact that the prover doesn't know delta, right? So that is rather annoying. So and that's also what we looked at in 2023. We're thinking, well, we like this proof system is really great, right? So you really pay a very low overhead in terms of communication, and also what the prover and the verifier have to do in terms of computation on the VOLE correlations once they're there. It's really not much. It's just a bit of field arithmetic left and right. But it's designated verifier because the verifier has to keep this delta private in order for the proof to go through. Otherwise, you can prove whatever you want, and then it's not really a sound proof system. So is that really necessary? And that's when we are going to put the VOLE into the head, so to speak. So and here what we have to think about is, do you really have to keep delta private? And actually not. This is where animations in slide would come in handy, but well. So if you think about what is happening in such a proof system, well, first the prover who has the witness, well, the prover needs its share or her share of the VOLE correlation in the beginning of the proof, right? Because she has to do the proof. At this point, the verifier, I mean, it could get his part of the correlation, but at this point, it doesn't have any work to do yet, right? I mean, it can verify the proof in the end, but we don't really care. So actually, we just need the prover to get her share of the correlation. And she can do, she can send whatever she needs to send, right? She can commit to the witness, she can commit to the outputs of the multiplications, and so on and so forth. Then we have the verifier sends some kind of random coins if you want to do random linear combinations in order to open things cheaply. Yep, and that kind of finishes the proof overall. So at this point, all the messages that the prover would usually send in a VOLE-based zero-knowledge proof have been finished. And only then the verifier actually has to do some work, because only then the verifier really needs to verify the proof. Before that, it could always be delayed to later, right? So only then actually the verifier has to say, well, what about using delta as the secret at which you're going to evaluate the polynomial, right? At this point, when it chooses delta, well, the prover has finished her work. She already sent away the proof, right? So as long as we make sure that whatever the prover gets and the verifier gets from this correlation here is fine, like are really the evaluations in the polynomials, everything is good. Like now the prover can check that the proof is sound, and in particular, the prover can even learn delta, right? Because the prover has finished her proof. Like if we can reveal delta to the prover, like she can't mess around with anything in the proof here anymore. She could stop giving like parts of the VOLE correlation to the verifier, but the prover could always abort. You can always not make a signature. Okay, but that's great, right? So that's a nice observation, which means so we can kind of delay the whole part with picking delta and evaluating the polynomial to later. And this is going to help us to build these correlations in a nice way. So we don't really need like proper VOLE. We need some kind of VOLE where messages can be delayed, and this allows us to do this in a non-interactive way. And in particular, since delta is now something random, so these are public coins. Here are going to be public coins that the prover sends during the proof. This is actually going to give us a public coin, zero knowledge proof, so we can apply the Fiat-Shamir transform and get signatures the good old tested way that we know via the Fiat-Shamir transform. Yeah. Okay, so we don't really need a secret delta. That allows us to put the VOLE into the head. So we're going to add some public verifiability to this proof system. And as I hope I convinced you by now, once we have that, we actually have a signature scheme. And how does that work? Just a quick overview of how this works. And this is some theory funkiness that turns out to be really great to build a proof. So first of we'll first look at vector OLE, at building vector OLE using so-called oblivious transfer, and then we get rid of the oblivious transfer and see that this still works. Okay. And the key observation here comes from a paper from 2022, which is if you have n out of n secret sharing and oblivious transfer, n minus 1 out of n oblivious transfer, build a VOLE correlation over the field Fn for some small n. So how does this work? Well, the prover takes her secret, she generates her secret U, and she just additively shares it. So it just generates n random shares. Okay. And now she feeds this into this n minus 1 out of n OT, which means that the verifier will learn all of these shares except for the one at position delta. Okay, n minus 1 out of n oblivious transfer means the prover sends n messages into the oblivious transfer. And the verifier gets out all but one of them, and he can pick which one he doesn't want to have. Okay, this is something from like crypto protocol world that we all love. So how does that help us? Right? How does it help us that we have this oblivious transfer thingy in order to build the VOLE correlation? Well, so this additive sharing of U already says tells us how we will define our secret U later, namely just as the sum of all these random values, and the value V, which the prover also has to get independently, right? She's going to define it this way. She's going to multiply the first share of U with -1, the second share with -2, and then she's just going to add them all up over the field. And now what the verifier can do with his shares here, with these UI values, it knows delta. Well, it has picked delta. Okay. And now if we multiply, if we sum up all these UI values multiplied with delta minus I. So delta is the one thing he didn't have. He picked not wanting to have, and I is just the sum over the index over which we go. Well, if you expand this sum, you see that this UI that the verifier chose not to take. Well, at this point, this term here vanishes, right? So you don't need U delta in order to compute the sum. The remaining ones, the verifier can sum up. Now we define Q this way. And if you just take this sum apart, we actually end up with something that is U times delta plus V. It's just write it up on the whiteboard. Like that's also a one-liner. And this is the very simple observation. And that means if you can do this additive secret sharing and you can do this oblivious transfer, then these two sides can actually generate an oblivious linear evaluation correlation. Just out of nowhere. Everybody who does protocols knows that in order to build oblivious transfer, you need public key primitives, which is kind of bad because we want to build something from symmetric primitives only. But it turns out we don't need full-blown oblivious transfer in order to build this. As I said, we're fine with the prover actually learning the delta that the verifier is choosing, right? So what we can do is, instead of doing an oblivious transfer, we'll let the prover make a vector commitment to n random shares. And then it's going to send the commitment over to the verifier. So this is just a vector commitment to n random strings. The verifier says, open all but one of these commitments to me. And the prover is going to do that. And then we can turn this into a VOLE correlation, as I mentioned before. So now, as I said, the prover learns delta, but if we do all of this after the prover is done with her proof, we're still fine. And we know how to do these things super efficiently using GGM trees, like pseudorandom generator, where you go left and right and left and right. And then we also know how to do this opening all but one of them very efficiently in such kind of trees by using standard constructions where we reveal parts of the seeds. Okay, and also if we look at this here, like the prover can compute all of this independently of delta being chosen or not. So it can make its commitment and actually do its whole proof before delta is ever chosen. So it's actually compatible with how we want to do this proof. Okay, so that's actually the magic to VOLE-in-the-head. It's actually a very simple observation that that we can get these VOLE, that we don't really need full-blown VOLE correlations to do zero-knowledge proofs, and then we can get them using very cheap cryptography, which is just pseudorandom generators and hash functions, which is everything that you need to build vector commitments to random values. It's a tried and tested technique. Okay. So so what I mentioned to you here, there are a few caveats here. So you might notice that the field has to be of size n, which is the number of shares that you have here, right? And if we want to have proper security, we will later need that our field is exponentially large, and doing exponentially much computation is kind of something that we don't want to do during a proof. So there's a bit of work that we have to do. And what one can observe is that, well, if we want our field to be actually large, what we're going to do later is we're going to choose our fields to be like m being 2 to the 128. But if that is if this is an extension field of a smaller field, you can do some funky mathematics. There are people in this building who know more about this than I do, where you just you do a lot of voles over the same base field, and you make them to the same secret, and then you can lift that into the extension field of size 2 to 128, and then you can do your arithmetic there. And in order to get 128-bit security, that'll mean that you have to send 11 to 16 bits per AND gate that you later on have to compute. Like, that's the cost of doing VOLE-in-the-head instead of interactive VOLE. I'm not going to mention the consistency check because that's probably going to take too much time. Let's rather go to the fun stuff, which is doing signatures with this. Okay, enough of the math. So we then looked at, can we use this VOLE-in-the-head for something? And yeah, it turns out that it's actually giving us a nice way of proving that you know an AES secret key or a publicly known plain text ciphertext pair. And that you can then use as a digital signature, right? This is actually something that has been used before. For example, in the picnic signature scheme, where your public key is essentially, let's say, a plain text ciphertext pair for an encryption function, and the secret key is the block key K that was used to encrypt. And so when Picnic was first proposed in 2017, zero-knowledge proof systems that only were based on symmetric assumptions weren't as efficient as they are today. So instead, people made the proofs small by using encryption algorithms that were custom built for these proof systems, such as LowMC or MIMC, which was not always the greatest choice when it comes to security. Or people were using other assumptions, like code-based, LPN-based constructions or multivariate polynomials and so on. So this is what people have been looking into, and we thought, well, what about AES? You know, AES is kind of popular, and I think a lot of people say, well, AES is secure. We trust AES more than, you know, LowMC or MIMC or whatever. So what happens if we plug this into VOLE-in-the-head? Well, is AES actually friendly for being evaluated in a zero-knowledge proof system? And actually, yes. So I don't know what people, I don't know, I can't look into the head of the guys from Belgium who proposed AES back in the days. It has a very arithmetic structure, right? So everything that you do in AES, like the shift row, mixed column, add your round key, like all of these things are just linear operations over F2. These are all just kind of matrix multiplications. You can, if you could commit to the individual bits of an AES key, and you kind of make commitments to the input, then most operations in AES, if you evaluate the block cipher, are just linear operations. And well, what is the S box? The one nonlinear part that you have there, well, that's an inversion over the field F2 to the 8. So you take 8 of the bits together, you lift them into a larger field. And so, well, what is an inversion? Well, an inversion is actually just committing to the output and checking that X times Y equals 1, right? So field inversion is very simple to verify. Just check that the product is 1. Caveat, input to an S box can be 0, in which case the S box maps to 0 is something that we have to deal with later. Okay, so what that means, well, actually, this AES cipher is very, very friendly for being proven in zero knowledge if we can do these things very efficiently. And turns out we can. So what does it mean? In the zero knowledge proof, if we want to, for example, evaluate AES 128, we'll have to commit to the key. Well, that's our secret that we want to prove knowledge of, so we don't get rid of that. And then we just kind of commit to the states after each round, right? So each AES round is add your round key, do the linear operations, and apply the S box. So we just commit to all of these round outputs, and then we can just for the linear operations we can kind of back propagate until we are at the outputs of the S box, and from the previous round we can forward propagate until we are at the input of the S box, and then we just do the multiplication check that input of S box and output of S box together give you 1, and that's all we actually have to do in the proof. So what if the input of the S box is 0? So in the original FAEST proposal, we just made the prover choose a key such that this never happens in the encryption trace. Or we can actually get rid of that without any issues. Okay, how terrible am I doing on time? I have 5 minutes, great. So I'll just now do, everybody wake up. It's just almost lunchtime. I'll just give you the numbers. This is the short list of numbers. Please do not take pictures yet. There are more numbers that are going to come soon. So this was the original FAEST proposal. For signatures, we needed 5,000 bytes in small mode with 4.4 milliseconds for signing or verifying. Or if we want to have a faster but slightly larger signature, that's 6,300 bytes and 0.4 milliseconds for signing or verification. So that was the original proposal. So then recently we kind of figured that a lot of the costs in these proofs is actually making these vector commitments. So I mentioned that, you know, like if you want to generate a VOLE, you need to make random vector commitments to random values, and then you need to open them. A lot of cost in the proof system, therefore signature size, is just opening these vector commitments. So we found a better way how to do that. And then there are some other optimizations using rejection sampling. Ask me over lunch how it works. I'll not explain it now because we are very close to lunch and, you know. So that's one optimization that we did. So we tweaked the proof system to be more efficient there. And then we now also checked what happens if you actually use different encryption functions or one-way functions. So first we tested something that is called RAIN. RAIN kind of follows the same design as AES, but instead of having a lot of S boxes with 8 input bits and 8 output bits, it just takes 128 input bits and inverts them. Boom. Like that's your nonlinear function that you have right there. And turns out that this way, with 4 rounds instead of the 10 rounds of AES 128, you get a decent amount of security. So we implemented that. And multivariate quadratic polynomials are also something that people love. Like there's a lot of proposals for this new NIST call that use multivariate quadratic polynomials. A lot of them try to trapdoor these polynomials so you can build a zero-knowledge proof there. We just actually go with random instances of MQ problems, which is probably the hardest that you can get. So we checked what happens if you do this. So just this is the slides with the numbers. So if you wanted to take a picture, now is the moment. So this is the up there. You find the original proposal that gives you 5,000 bytes or 6,000 for the fast assigning. We figured that we can actually do proper AES without this no zero input to S box with the same signature size and only like, I don't know, 100 microseconds more signing or verification time. So cool, we get the actual security of AES without any extra cost. Our improvement of FAEST is called Feaster. Well, no comments. So in comparison, so this thing now, in comparison to the original FAEST, it has 500 to 500 bytes less of signature size, or for some instances even more. And the signing and verification time also went down to 0.4 milliseconds or 3.3 for the smaller signatures. Then if we apply our VOLE-in-the-head to RAIN, we got something that we call Mandarain. Now this gives you signatures of between 3,100 and 3,800 bytes, signing and verification time below 3 milliseconds. And if you use MQ, well, that actually allows us to get the signature size down to only 2.5 kilobytes using, let's say MQ instance that is for current attacks, hopefully as something that gives you 128-bit security given current attacks. Where I want to stress, this is not some trapdoor special MQ instance. This is just random MQ instance. Yeah, and also there, less than 5 milliseconds for signing or verification. In comparison, and the only fair comparison would be to compare Sphinx with, let's say, the original with this FAEST full key, right? Because this is the only one that is as secure, right? Sphinx Plus uses only hash functions to get to give you signatures. So so here Sphinx for I think I got the S and the F block wrong, but so the fast Sphinx instance for 128-bit security on the same machine would need around 4.4 milliseconds for signing, very fast verification time, but signatures in 17 kilobytes. And for smaller signatures, you would have 7.8 kilobytes and 88 milliseconds for signing, right? So FAEST full key wins here in both sides, in both of these choices. But I want to stress, of course, we make the extra assumption of using AES, right? Sphinx Plus doesn't need that. And of course, if you're in a setting where verifier time, small verifier time is much more important than small signing time, Sphinx is also the better choice because, I mean, it's hard to beat that. Like we don't get to something as small to like 150 microseconds. right? But if you need anything else than a scenario where the verifier is a lot weaker than the prover, then looking at FAEST is actually maybe something good, because we only need assumptions that we hope are fine and tested. So VOLE-in-the-head zero-knowledge proofs are they are linear size proofs, so linear in the size of the statement, but rather lightweight. And with this VOLE-in-the-head technique, also publicly verifiable, meaning we can build signatures from it. FAEST with only hash functions and AES as block cipher is arguably a very conservative design for a digital signature scheme, so no new hardness assumptions that we need. Performance is reasonable, right? We're not as fast as some lattice-based constructions or so, but given that it has a very conservative design choices, maybe it's a trade-off people want to make. And then we made some more recent aggressive optimizations using MQ and RAIN, right? And these give you something that gives you better performance, but maybe not as secure as you want to have. If you want to know more, there's our website, faest.info, where you can get more information. And otherwise, thanks and enjoy your lunch.
Thank you for the talk. I know we want to go to lunch, but are there any like small questions? If not,
thanks for the talk. Are you planning to update your NIST submission with these other assumptions and so on, or is this more like application of the transform?
Good question. Thanks. So this updating a NIST submission you can only do we can only do that if we progress to the next round of the NIST competition. We don't know which schemes will progress to round 2 yet. If we do, we will likely update our submission with something more fun. Even though I guess we will leave the old AES based in there, because that's the selling point of FAEST, right? If you want to make more aggressive assumptions, you can use other signature schemes that are probably a lot more performant. But if you want to have something conservative, then this is fine. Yeah, we will going to update them if there's ever a round 2.
can I ask one question?
Yes.
Thank you for the great talk. And can you go one page before this?
Yep.
Where you had all the numbers. I was just wondering, so you kind of mentioned that it's the number of ands that really kicks in for the size of the signature.
Yeah.
But for these, I guess like the underlying field that you use are different for each one-way functions. How does that impact the size? Just about
the size of the field.
Oh yeah, field.
Actually, the size of the field is so you need to do your check later in an extension field that is big enough. So that's and that you have to pay. You have to communicate something that is proportional to the size of the log of that field. For every witness bit, and then for every multiplication that you want to check. And that's also why, for example, the MQ-based stuff has so small signature size, because all you actually communicate there is the witness and nothing else. So that's kind of the minimum.
Okay, thank you.
Thank you for this great talk. So I had 2 questions. So when you mentioned that AES was zero knowledge friendly, so for example, would that also have been the case for like SHA-2 or Shake?
I think we never tried those. Simply because I guess I think people implemented SHA-256 in one of these proof systems at some point, and it's a factor of I think it was a factor of 5 or 6 that the statement gets bigger, so not great. Yeah, so I think people just look at block ciphers there because it's more performance, better performance. Yeah.
Okay, and I had a second question. So I think it was Kales and Zaveruka. They proposed the idea of using reverse multiplicative friendly embeddings to do like some sort of packing, and they will obtain some improved performances. Do you know if that would be compatible with FAEST?
I think not, because these usually work over rings, right? And VOLE-in-the-head works over fields. So RMFEs are for ring extensions, but maybe there's something you can gain from that. But I don't know. Like, I think other people have looked into this and they know more. I think there's a paper on applying RMFEs to VOLE. I'm not sure if it works for VOLE-in-the-head. So I don't think you can gain enough when we talk about signatures. So.
All right, thank you. Are there any final questions? Okay, one last question.
So I was checking the status of rain. It's got 2 rounds up to its attack.
Sorry again?
Rain
Yeah.
is attacked up to 2 rounds in the recent FSC paper.
Yeah.
So it's only 1 round left. So what's your comment on that?
Oh, yeah. So my comment is that I'm not a symmetric key person, so I cannot give you any reasonable comment there. We used 4-round rain. I mean, we also benchmarked 3-round rain for how we wanted to try something here really that is just to see how fast or how good these signatures are when you throw in a one-way function that is a bit less conservative. I'm not going to complain about like the work of my co-authors like Christian Rechberger, who have proposed rain. So I can't really say anything about the security of 3-round or 4-round rain. But if you want to be more on the safe side, I guess you would go for the MQ-based construction, because I guess MQ has been studied a bit more than rain, I would say.
Yeah, let's thank Carsten again.